Okay, so here's my board code. I've got an n by n two-dimensional array of integers that stores black, white, or blank, which represents the board state. I have children, and I also have a score. I also have a parent property that I may or may not be using. So here I have a dynamic n, so I'm going to use a smaller board just for the sake of this demonstration, but I can set it to 9 for normal stuff. Okay, so if I want to calculate the next states, I say, do I want to put a black or a white piece down? I go through each column starting at the left and look at the bottommost slot in that column and say if it's not already occupied, then fill it with the color that I'm trying to fill it with, and break, because once I put something in a column, then I'm done with that column. So there are at most n possible next moves. There would be fewer than n if we had already filled up some of the columns. The way that you get the score is you get the black score minus the white score. The way that you get score for a particular color is you check and see if that you start at the top left corner and you look down to the right and down to the left diagonally and down to the right diagonally. The reason that you can look in only one direction rather than also up is because you proceed from the top row and you go down. You don't want to double count. So that's the scoring mechanism. Now minimax looks like this. So we recursively go down in a depth first search manner, into going down through the children, subtracting 1 from the depth each time until you get to the leaf node, which is the bottommost ply that you wanted to consider. You get the score here, and this is my performance enhancement of only calculating the score at the leaf nodes and then percolating that score up. So you say get the leaf score and then take it up to the level 1 above that, and set the score to that best value. If we're at a maximum, we want to pick the maximum of the minimum nodes underneath it. If we're at a minimum, then we want to pick the minimum of the maximum nodes that are underneath that. So that's minimax. The alpha beta code is extremely similar. It just has this additional alpha and beta. So we keep track of a global alpha and beta score. So again, we percolate down until, in depth first search manner, until we get to the leaf node, which is at the depth that you want the ply to go. You calculate the score at that point. You percolate that up to whatever it's called. So let's say that was a beta. So we say beta is the minimum of basically maximum integer or positive infinity and what you just calculated for the child. So you set beta to be that value, and then you percolate that up. So once you're done with those children, you would percolate that up to those parents, which would be the alpha score. So you'd say it's the maximum of those minimum scores, and then etc. So alpha keeps track of the best global alpha, and beta keeps track of the best global beta. So at any point, if alpha is greater than or equal to beta, except for at the root node, because I'll tell you why in a second, then you need to break out of this code. If you're at the parent, then basically you need to keep checking, because essentially otherwise you would go all the way down the left and you calculate, maybe it's -2 and it goes all the way up, -2 alpha, -2 beta, -2 alpha, -2 beta, -2 alpha, and at that point alpha equals beta because you're at the root node, and so you would potentially stop searching the tree altogether, but that's not really what you want to do. You want to make sure that alpha and beta is really referring to an ancestor. So in this case, since there is no ancestor, you have to not break at the root node. Okay, so now I'm going to show you the code running really fast. So it's under apply, pruning true. Okay, remember I can set the board size to be whatever I want. So here's 1, 0. So my strategy is generally to try to build it up as much as possible, but black won anyway, so there you go.